Imagine you're playing a game with your friend. There are 2 blue and 2 red marbles in the bag. Now you draw a marble without looking. If it's a blue marble, you win. If it's a red marble instead, your friend wins. Your friend suggests making it a little more exciting. If he wins, you should give him $1. If you win, he would give you 80 cents. That's not fair, is it? You don't need a PhD in statistics to see that that would be a bad deal for you. But what if we add 1 red and 3 blue marbles to the bag? There are now 3 red and 5 blue marbles in there in total. Would you accept his proposal? It's now way more difficult to make an intuitive decision, but luckily a simple mathematical concept can be used to assess the situation. Imagine you were to play 100 times. Sometimes you would win, sometimes you would lose, and so on. You play 100 times, and since you win with 5 out of the 8 marbles, the probability of winning is 5/8 for you for each time. So, on average you would win 62.5 times. You get 80 cents for a win. For 100 games, you can expect to win $50. But you would also lose. Since you lose on 3 of the marbles, and each time $1, you would lose $37.5 on average. If we now add what we lose to what we gain, we get the expected profit in total. Instead of 100, we can simply multiply the terms by 1. We get the expected profit per move, also called expected value. As you can see, we simply calculate it by multiplying the probability of winning by the potential gain and adding that to the product of the probability of losing and the potential loss. In our case, the expected value is 0.125. That is 12.5 cents. For each round, you can expect to win 12.5 cents. If you now decide to accept the offer from your friend, you are acting according to the theory of expected utility. According to this theory, a rational decision is the one with the highest expected value. However, it does not always have to be a monetary value. It can, for example, also be a matter of lifetime or happiness. This is why we do not speak of profit or value within the theory, but of utility, depending on what we want to maximize with our decision. However, a choice can also do more harm than good. Then we speak of costs. Decisions can also be represented by a decision tree that models the expected costs and the expected utility. Whenever you have to make a choice, you find yourself at a decision point. Labeled lines now extend from this decision point, modeling our possible decisions. The lines lead to events that the decision maker cannot influence. All possible outcomes of this event are again represented by labeled lines. The respective outcomes are supplemented with their respective probability depending on the decision. In our situation, the decision tree looks like this. We can decide not to accept the offer. Then certainly we will have no costs, but also no utility. But we can also decide to accept the offer. Then, with a probability of 3/8, we have a loss of $1. But with a probability of 5/8, we have a profit of 80 cents. If we now add up the individual expected values of the decisions, we again arrive at an expected utility of 12.5 cents. Here is another example. Imagine you are a doctor and you have to consider whether you should perform a knee surgery. This is your decision point. The decisions you can make here are to operate and not to operate. According to expected utility theory, a rational decision maker should now consider every possible outcome for the decision. For the sake of simplicity, let's assume 4 possible outcomes for our situation. If you don't operate, there is the possibility that the knee will return to full function on its own, but there is also the possibility that the knee will not become functional again. On the other side, surgery can improve the functionality of the knee. However, it's also possible that the operation will fail. The knee will then be even more damaged than before. Next, we assign a utility value to each of the options. An assignment of the respected utility values could look like this. The utility values are ranging from -100 to 100. 100 represents the highest utility we can have. -100 the highest costs. You might argue that if the knee is operated on and heals, it will still function slightly worse than when it were to heal on its own. The worst case scenario is if you have the operation but the knee then functions worse than before. On the other hand, it's less bad if the knee is not operated on and remains in poor condition. Now, think about the probabilities for the individual outcomes. You determine these based on your medical experience. You consider that if you do not operate, the probability of a spontaneous recovery is 30%. We add 0.3 to our decision tree in order to be able to calculate equally well. Since we only have 2 possible outcomes per decision in our example, the probability of the knee remaining in poor condition is therefore 70%. The probabilities of a path of a decision always add up to 100%. Because once you have made a decision, something has to happen. Now you estimate the probabilities in the event that you operate. It's a difficult operation. You assume a 65% chance of success. We have now fully modeled the situation using a decision tree. How do you decide? According to the theory, we now calculate the expected benefit for each decision. We proceed as we did with our situation from the beginning. We multiply the expected outcomes by the probabilities. Then we add them together. We calculate the expected utility. In our example, the expected utility is higher if we do not operate. So, if we decide to do so, we act according to the theory of expected utility. Even if we can make more decisions than 2 at one point, or if there are more possible outcomes, our procedure remains the same. We calculate the expected value for each decision and then compare them. It is important to note that depending on which utility values and probabilities you assign to the events, the recommendation of the theory can change. It is therefore important to estimate these parameters as well as you can, but even if we are not so systematic, these parameters influence our decision even if we are not aware of it. Expected utility theory and visualizing situations of choice using decision trees is a good way to systematically make us aware of the situations in which we make choices and therefore making better decisions. And this is great.